Hey everyone! Today I want to do something totally different. Rather than give you a lecture on the background to my field of research, we're going to dive right into the lab and do an actual experiment. We're going to make ourselves some graphene. What we're going to do is use some chemical trickery to turn graphene oxide, which is a brown non-conductive material, into something more like graphene, black and very electrically conductive. What's neat here is it can all be done using not too hard to get materials, with basically no specialist equipment whatsoever. Graphene oxide is made by adding lots of oxygen atoms to graphite, in a rather nasty process known as Hummer's method. The general name for the chemical process of adding oxygen atoms is, unsurprisingly, oxidation. Luckily for us, this is basically an industrial production technique. So, rather than buy all the horrible chemicals needed to do it ourselves, we can just buy graphene oxide online, by the barrel load. The oxidation of graphite is what changes its colour and stops it conducting any electricity. In that sense at least, graphene oxide isn't actually much like graphene at all. This is why a lot of researchers treat graphene oxide as an entirely separate material to graphene. Graphene oxide is actually a really nice material to work with because it readily disperses into water, unlike unoxidized graphene. Water is nice because it's non-toxic, evaporates away quickly, and can be mixed with other materials to make composites. This works because the oxygen-containing groups of atoms on the surface and the edges of the sheets are chemically very similar to water. The reverse process of oxidation is called reduction. There are a few ways that graphene oxide can be reduced, including the use of extremely high temperatures, or microwave or laser radiation. More on that another time. The chemical method we're going to use involves one simple, very safe chemical, vitamin C. As you'll all know, vitamin C is a naturally occurring chemical found in citrus fruit. It's a very weak acid, chemically related to sugar. It attacks two specific chemical groups in graphene oxide and can turn it back from a brown insulator to a black conductive 2D material. Okay, let's get started. First, we're going to measure out 4 grams of our internet-purchased graphene oxide dispersion. This particular stuff has a concentration of 25 milligrams of graphene oxide per milliliter of liquid. So, we actually have about 100 milligrams of graphene oxide here. The next step is to dilute it a bit because the stuff is quite thick. We'll add 12 milliliters of purified water to reduce the concentration by a neat factor of 4. The next step is to add our reducing agent, vitamin C. We'll add the same weight as we have graphene oxide in our dispersion, 100 milligrams. It will dissolve very happily, but it's basically impossible to see this happening because of the colour. The next step is to seal up the bottle so the water doesn't evaporate during the reaction. We place our sealed sample in an oven or on a hot plate. The temperature is set at 95 degrees Celsius, just below the boiling point of water, and left for 2 hours. As you can see, over time the brown colour starts to darken to black, and the material which used to be well dispersed in the water starts to shrink into a pellet. Once the reaction is done, we can unseal and extract our blackened lump. This spongy material is full of trapped water. We can work out exactly how much reduced graphene oxide there is compared to the water by weighing a sample before and after we've dried it out. It's a very, very small amount in this case. About 7% of the weight of this block is solid, the other 93% is water. If we poke the surface with the probes from the resistance meter, we find that our black mass is now very conductive. Crunching the numbers gives a conductivity of around 1 Siemens per meter. Doesn't sound all that impressive. But, as a comparison, the purified water we used in the experiment should have a conductivity of 10 to the power of minus 10 Siemens per meter. Our simple recipe has given us a reduced graphene oxide cake which is 1,000 million times more conductive than purified water. It's also only about 10 times less conductive than other researchers manage using a highly optimized process. Call that success. This is a really neat and simple way to make electrodes for supercapacitors, which I know I talk about a lot. I'm very interested in making new energy storage materials as this goes hand in hand with the use of renewable energy sources. Supercapacitors rely on having electrodes with very high surface areas, and these reduced graphene oxide cakes are perfect candidates. To produce a supercapacitor, we would need to add an electrolyte to the system, such as a strong acid, and make two pieces that can be separated by a thin, permeable, but not electrically conducting spacer layer. We could think about adding some polymer binders and an additional acid electrolyte to our starting mixture. These extra materials will get trapped inside the reduced graphene oxide cake as it forms. The separator layer could be something as simple as a plastic filter membrane, which prevents electrical contact when the two reduced graphene oxide electrodes are squeezed together. So simple. The performance we get from a system like this is very strongly dependent on a lot of factors, and very good results have been achieved previously with this kind of technique. But even without going this far, what we've managed to make with very little effort is still impressive. In the future, we'll try making some devices and seeing how well they work. See you next time! Thanks for watching, everyone. If you like what I do, please consider supporting my work via my Patreon page, where you'll have access to a range of in-depth discussions on the physics, chemistry and engineering of nanomaterials. If you'd like regular updates, please subscribe and like the video. It helps so much, and I look forward to talking to you again soon.